Hello everyone, it's great to be with you and welcome to the next part of our OpenARK tutorial at IEEE ISMAR 2022 in Singapore. I'm Mohammad Keshavarzi, PhD from UC Berkeley. I'm an R&D consultant and strategist for metaverse startups in Silicon Valley and San Francisco Bay Area. The tutorial is a continuation of what we presented during our previous ISMAR tutorials, where we aim to share our main research elements in generative modeling and spatial computing. Today we'll be presenting some of the ongoing research we've been doing at the FHL Vice Center and XR Lab at UC Berkeley, and we hope to introduce methods that you guys can also implement in your applications or research in spatial computing. Okay, so let's get started. Let's get started with the term spatial computing. As you all know, spatial computing is kind of an umbrella term for augmented, virtual, and mixed reality modalities. The word itself can be described as computing in a spatial context, and it comes with a virtual and a physical component. The virtual component is the closest we can get to the concept of the metaverse. It's unlimited in space, you can go everywhere, you can virtually move around, and it's unconstrained physically from various surrounding built environments we have in our real world. The physical space, on the other hand, is pretty much constrained by contextual and functional requirements of our surrounding real world environment. And for us to develop a successful spatial computing application, we would need to address both the virtual and also the physical component of this modality. So when we're talking about spaces and everyday spaces that our spatial computing applications are going to be executed in, we should highlight the fact that there's much diversity in the geometrical and also functional aspects of our everyday spaces. Geometrical aspects such as size, layout, and material, and also functional aspects such as whether it's a workplace or it's a residential space, or even inside a residential space, whether it's a bedroom, kitchen, or whatever. Each of these target spaces which spatial computing experiences are supposed to be executed in have their own different properties and would need us to address and adapt to them. Yet, when we think about future AR applications, one of the main challenges that we can highlight is that there's somehow a design barrier between the metaverse developer and the users of the spatial computing applications. The idea that the developer doesn't actually know how its design or implementation is going to work in the target rooms. It doesn't exactly know the open spaces, it doesn't exactly know the boundaries, where the walls are, where the furniture is. And that makes it really hard for them to design a unique experience, or the experience actually they want for the target users, which are pretty much in an unknown space for the metaverse developer to experience. But this is not actually the first time we're having this problem, right? We've had this before. It's not only a challenge in 3D, it also was a challenge in 2D. The idea that a developer doesn't know or didn't know what target display is actually developing for, whether the end user is holding a mobile phone, tablet, or desktop. And the idea of responsive design aims to address this issue, right? So the fact that you write one code base and it automatically adapts to different display and screen sizes is the concept of responsive design, allowing the developer to have some kind of a communication between what it can be potentially designing for and what is actually developing in terms of its code base. Now, there's a lot of differences between 2D screens and 3D screens, and it's not really a similar, it might be a similar problem, but you can't use the similar implementation of responsive design and take it from 2D to 3D. 2D screens are usually rectangular, open spaces, open shapes, and our 3D environments usually come with obstacles, irregularities, and all much more complexities. So we can firmly state that this design barrier is something that we need to address in future AR applications. But it's not only the fact that one developer for large-scale deployment is having such issues, but actually when we're talking about applications which multiple users are using in spatial computing context, the fact that each of these users are not aware of the other spaces is also a major issue, especially for telepresence applications. So what we'll be talking in this presentation and tutorial is sharing some techniques and methodologies we thought that can address this problem using contextualized spatial computing techniques in a generative approach. What we try to do is basically facilitate an adaptive process for spatial computing development. And in this regard, this presentation, we're going to talk about two topics. The first one on the left is about large-scale deployment for diverse environments, the idea of how can we come up with a technique or set of techniques that one code base developed by a metaverse developer can be basically augmented to a large-scale set of diverse environments. And the second one on the right is going to be how we can conduct telepresence from a spatial point of view in diverse environments. So let's start with the first one. And we can also look at this issue as a content augmentation issue. So when we want to do content augmentation for a similar space, for a sample space, we basically want to add an object to a space in its most simple way possible. So let's just say we want to add a sofa to this place. On the left, you see a plan view, and on the right, you see a perspective view. Hypothetically, the sofa can be placed anywhere in the space, right? As long as it's using very general rule of thumb physical constraints that it can, should be on the floor. It can go everywhere. The problem is you may have some conflicting and inconsistent issues with the context. On the left, you see the sofa is basically conflicting with the other geometry of the context. And on the right, you see that there's no geometrical conflict, but it's more inconsistent with the functional constraints that we usually hold within such rooms. So let's talk a little bit about the methodology. The way we looked at it was if we have a target room, the idea is can we turn that into a graph? And by graph, we want to calculate the bounding boxes of each room and have each of these bounding boxes as a node of this graph. And the edge of the graph would be topological relationships of positional and orientational matter. For instance, whether an object is in the middle of the room, is in the edge of the room, and also whether it's close to the other object or not. Also, object and room relationships, whether they're in a similar direction, whether it's facing other objects. And all these together would actually be represented as one single graph for each room. Now, when we want to add an object to a room, augment the content, we can initiate different graphs for this content augmentation criteria, right? And the goal of our workflow, the goal of our system is to find which one of these graphs actually come with the highest probability of scene plausibility, meaning that which one of these graphs would probably be a graph of a real room. The way we train this is basically by creating a knowledge model. We look at the Matterport 3D database and learn from graphs and input them in a knowledge model. The dataset, as I mentioned, is from the Matterport 3D. Of course, there's different types of datasets out there, from synthetic datasets such as SunCG, and also datasets that can be generated from computer vision tools to extract 3D bounding boxes from 2D images and so on. The reason why we use Matterport 3D when compared to synthetic datasets was the natural environments and the human correspondence of natural environments to synthetic data. And of course, at the time of this presentation, we felt that the 3D object detection or basically 2D to 3D bounding box techniques were still not in a position that we could have utilized for our large-scale training. So here's an example of the positional relationships and orientational relationships from the Matterport 3D dataset. You can see, for instance, like on the right, the bed is usually, in most cases, towards the center of the room. You have storages that, mostly in the edge of the room or the center of the room. These are object-to-room relationships. You have on furniture-to-furniture relationships, for instance, chairs facing chair facing tables. And coming up with these relationships would give you some very probabilistic viewpoint of how objects are arranged in a general scene. So this is a very general workflow. On the left, you see scene priors coming up to the knowledge model. On the right, you see that sampling method that we talked about. For each furniture, we want to sample different possibilities, and the idea is, using a KDE model, we want to see which one of these graphs is highly plausible to be a real world space. So let's talk a little bit about our experiments. Here's a sample room, and we want to add basically a bed. This is a graph, and over here you see the probability map. The darker the result is going to be the higher probability, which would be the center of the object to be placed. There's also a probability map we're rendering over here in the orientation of the object, and as you see, the system calculates this would be possibly be the best location for an augmented bed for this room. Other examples over here, as you see, we see a living room augmented by a sofa, or a workplace augmented by an office chair, coffee tables, and also storages are all examples that you can see in this slide. Using this system, we can also do multi-object placement, basically placing and augmenting objects one by one. So if this is a target space of a room, which you see storage over here, a nightstand, and 2 sofas and a coffee table, if we want to add multiple objects, our system can do this one by one. And as you see, this is the probability map of each of these objects, a bed, a storage, and a sofa. And when we compare this to the ground truth, and actually what the data set holds itself, we kind of see some similarities and differences. In general, the location of these objects are placed in a different position and location, but you kind of see both of them are look functionally correct and probably plausible. So the fact that SceneGen isn't exactly augmenting the objects when compared to the test ground truth is the fact that it can be plausible, but it's not necessarily exactly in the same position of the test space. Here's other examples of multi-object placement. As you see on the left, they are partially empty rooms trying to be augmented with furniture. So let's get to our numerical experiments. The experiment that we conducted, as you may also notice in previous examples, is the fact that we get the ground truth, we choose an object, we take out the object, and then we give this scene and the object to the system, asking to do scene augmentation. And at the end, we compare the distance error between our scene augmentation prediction and also the ground truth. So here you kind of see the results of cumulative distance errors between the original position and the top position on the left. And also to make things more fair, we also calculate the closest top 5 positions for all predictions. This is basically ablation studies showing different components and different architectures of the scene gen system that we describe in our paper. And at the end, we naturally chose the best architecture for our system using different components and also different relationship elements and constraints that we explain in our paper. For the user experiments, which we thought would be a supplementary to the numerical experiments, we came up with a user study that we reconstructed rooms in the Unity interface, and we asked participants to get engaged in our study in a way that the object would be placed in different types, and the user would basically give a rank of how it thinks this scene augmentation ranks from a value from 1 to 5. Now, for this to be a fair study, we showed the user different implementations of the scene augmentation. The first one is basically a random, which we call level 1. The second one is going to be level 2 of open random, so the object is going to be just placed in a random orientation in an open space. Level 3 is going to be scene gen, which would be our system working as its best. Level 4 would be scene gen with its height map, and level 5 would be the ground truth. So in this study, we'll be basically randomly showing each of these levels to the users and comparing how the users saw each of them. So this is our interface. The user would click on add furniture, and the furniture would be placed in the room. It would have a top-down view of a plan view of what it can see, and on the right it would have 2 perspective views. And on the top you can see from 1 to 5 it rates how plausible the added furniture is. So let's get to the results. It's very interesting that users, as expected, gave very low performance scores to level 1 and level 2, which were random placements of the object. But when we compare level 3, which is our scene gen system, and compare it to the ground truth, you kind of see some very close similarities in terms of the Likert rating, and the scores of which the users gave. It's also interesting when we compare different furniture in our scene augmentation system. For most furniture, users rate scene gen and ground truth in a very close manner, except for objects like chairs, which you kind of see there's a very large range of scores, both in scene gen and ground truth. And of course, it's interesting to kind of think about it that chairs can be generally placed everywhere, and it's hard to really understand where a plausible positioning is or not. This other simulation, well, actually, this other plot also shows the top. I'm sorry, but I have to add more information on this slide, but it actually shows the top predictions of scene gen when compared to the top user preferences. So the idea of this slide is the fact that we asked the users after they did their Likert scoring to position the object in where they think it's the best position, and that would be the red points, and the green points would be scene gen's positions. For instance, in B, you kind of see that when the users wanted to add another sofa in the room, they gave 2 locations from their preferences. Half of the users one location, the other half the other location. And you kind of see that SceneGen also predicts the same in its 1 to 5 preferences. On image C, a coffee table was asked to be added, and you kind of see also the different locations that SceneGen aims to add its prediction towards. So after conducting and developing SceneGen, we thought it's very important to show an augmented reality application, as it was one of the main components and concepts for this work. I'll show you guys a video. Okay, so as you see, this is scene augmentation in its manual mode. No systematic augmentation happens over here. It's generally like what you get in an IKEA app. You add the objects and you have to rotate them and place them correctly. But when we do a similar thing with SceneGen, we already have a heat map and the objects are placed in a potentially plausible location for the users to interact with and also adjust later on. Okay, so when talking about SceneGen as an example-based scene synthesis method, it's really important to also address the fact that one main element of success is the fact that what data it's trained on. This is a very general point of view that for learning data, we have very much diverse and high quality data sets for 2D interfaces, but for 3D, this is not the case. At the time of this study, when comparing synthetic data and scanned data, such as SunCG and the Matterport 3D, we had a lot of differences when comparing these two. The synthetic data of SunCG had more than 45,000 spaces, houses, and scan data sets of Matterport 3D only had 90. So we developed this system called GenScan of seeing if we can augment this data in a more sophisticated way. The idea of GenScan is if we input a 3D scan, if we take a fully scanned building as input, and by automating the parametrization of the architectural features of the scan, we can output alternative layouts of the same building. In other words, given one single scan, we can generate tens of alternative scans using our parametric data augmentation process. So how do we do this? In the first step, our proposed system extracts the floor plan of a given scan by utilizing FloorNet, a hybrid neural network which takes point clouds and 2D images from the scan as input and outputs a predicted vectorized floor plan. However, applying transformations on discrete elements of the floor plan can result in inconsistencies. So to address this, we develop and apply a parametrization function to allow wall systems to be continuous and avoid unwanted disconnected spaces. Each line element corresponds to a pair of nodes, and when a transformation is applied to the line elements, the nodes also change position following their corresponding line elements. From the floor plan extraction, we can predict the location of the walls and boundary elements of the room. And with that, by applying transformations to the parametric floor plan, its corresponding mesh walls can also parametrically follow the same transformation. Again, if we take a closer look, by only moving the wall, we can cause geometrical and topological conflicts with the furniture, as you can see over here. And therefore, to address this issue, we develop additional procedural models for the movement of the furniture cluster. we calculate the bounding box, and by assigning the bounding boxes to a corresponding adjacent wall, we're able to move the furniture clusters accordingly and avoid geometrical conflict. Using this process and applying transformations to the floor plan, we are able to generate a wide range of alternative spaces using a single mesh as inputs. To show examples of the resulting output, we apply our algorithm on real-world scan datasets such as Matterport 3D, which is captured by the Matterport camera, and also FloorNet, which was scanned using a Google Tango phone. So on the left, you see input scan. On the right, you see the manipulated alternatives of the input scan. In addition to mesh manipulation, our system also generates alternative texture maps for the augmentation process. To do so, we use a pre-trained style transfer technique to incorporate alternative styles into the current texture maps. We also apply various color tints to the transferred texture maps. And interestingly, by applying new texture maps to the mesh, as you can see in this figure, we can generate a wide range of alternative scan quality geometries and textures from just one single input scan. Okay, so with this challenge in mind, we had the idea of, can we improve the models we developed in our previous project in SceneGen for populating parametric 3D scan data sets. And so to recap, we train a model using scene graphs, and then we want to calculate the best plausible, the highest probability of a plausible placement in a set of sample inputs. Previously, we talked about how we use the KDE model, and as a further step, we developed a system that incorporates the parametric modeling called GSACnet. Now, GSACnet, other than the parametric augmentation, it also uses a more sophisticated architecture that we utilize, which combines graph attention, Siamese, and autoencoder networks for the scene augmentation task. So here's some examples of the bounding box manipulation of the sample rooms of the Matterport 3D dataset via GenScan. So this was basically using GenScan, the parametric augmentation of one single augmentation that transforms one single room to multiple data points. As you see on the top, it's just input of one room. The bottom is also input of one room augmented together. And here are some scene augmentation results for GenScan. Still, of course, this project is currently ongoing research, so not the best visuals and not the best renderings. But again, if we go with the same performance metric experiment of taking an object out and putting the object in and doing a distant error calculation, we kind of see that GenScan outperforms the state-of-the-art scene GraphNet scene augmentation systems in various furniture models. So to really understand whether GenScan as a data augmentation model can be utilized and have impactful results, we also did another set of experiments seeing which type of data augmentation method would facilitate and improve distance error results of scene augmentation. So here we'll just call the Matterport 3D dataset as mregular. When we combine the Matterport 3D dataset with GenScan data augmentation, we'll call it MGS. Doing MGS with the area check, just making sure the room isn't larger than a proportional function, we call it MGSAC. And also using MGSAC and basically augmenting the data set by removing one object by each other, we call it MGSAC4. So as you see in this slide, MGSAC is actually outperforming the Matterport regular data set in both T1 and T5. And just as a recap, T1 is going to be the highest probability calculated by the scene augmentation system, in our case GSACnet, and T5 is going to be the best distance error or the smallest distance error in the top 5 probabilities calculated. Okay, so we talked about contextualizing systems for large-scale deployment for diverse environments. Let's continue our presentation with the idea of telepresence and telepresence in diverse environments. So I want to start by basically sharing an inspiring slide, which I was personally inspired in 2016. The work is called Holoportation. It's one of the early, not early, but one of the well-developed example of how telepresence can be utilized for collaborating with each other and basically meeting our loved ones. What I also always mention when sharing this slide is the level of realism the user experiences from the present standpoint. The fact that the presenter Shahram Mizadi actually takes one step back over here for his daughter to actually move around is personally very striking for me. The fact that it really feels his daughter is over there. It can be very helpful for next generation communication and really bring down the barriers of long distance relationships with loved ones, and also multiple factors in high-end workplace communication. Okay, so after looking at the slide, and again talking about the inspiration, it's really important that we really look at how the system works and what are the constraints and what are the challenges this system has. If we pause the video for a second, we do see some critical issues. First of all, the amount of open space allocated for this experience in both rooms. So on the top left, you see the room where capturing takes place for the little girl, and the main screen shows the user space where the user with the headset is actually there. Both spaces are pretty large. I'm not sure if in everyday spaces we would be able to have this much large open spaces available for us. At least in our apartments in San Francisco or many other cities in the world, this cannot always be the case. The second factor which I want to highlight is if we look closely, we see some markers on the room. And this really shows that there's already been some level of calibration between two spaces. In other words, the developers of this experience knew what each space looked like. But as discussed before, the diversification of our spaces and a lot of privacy issues, accessing these spaces of each other's spaces may not be really feasible in everyday experiences. And if each time we wanted to manually calibrate our surrounding furniture for each telepresence experience, it would be very challenging, mainly with the fact that we don't know what other spaces or participants even look like. So it's fair to say, with our current real-world environments and surrounding, collaborative spatial computing has spatial limitations itself. And I actually want to open up this problem a little more. Let's say we have 3 users, user A, user B, user C. User A resides in this very large living room. You can see a perspective view on the left and floor plan view on the right of the large room or space which user A resides in. User B, however, wants to join the telepresence meeting from her small office space. And user C is working from home and is planning to meet in his bedroom space, which has a little open area for others to join. So let's look at the first problematic scenario where spatial collision occurs when participants show up in each other's spaces. Let's see how. Okay, so this is user A's room, and as he's hosting the meeting, which augments virtual avatars of user B, user C, in an open area of this pretty big living room. If we hold the same positional relationship with each other between user B, C, and A, we kind of have problematic issues in other user spaces. In user B space, she actually sees no one, basically no one, because if you look at the floor plan view on the left, the other two users are located outside her office. You see, when keeping the same positional relationships with each other initiated in the previous scene, they just don't fit in. And in user C space, there's more weird things happening, where user A is looking like a ghost stuck in the wall and the dresser, while user B is also colliding with the furniture. Both of these remote individuals and their avatars are in undesirable locations. So you may ask, why do we need to keep the positional relationship constant? Why can't we just, have each user have the option to force position and manually identify a desirable location for remote avatars to be augmented in its space? So let's actually see what happens. Here we have the participants holding constant positional relationships with each other in all rooms. Let's just allow them to manually force position remote avatars in their own preference. And here's the problem. When user A is looking and talking with user C in his own room, shown on the left, so let me say again, sorry. When user A is looking and talking with Mr. C, user C in this space is actually not being looked at. It's as if user A is looking at the wall in user's B space. And a more weirder thing happens in user C's room, that user A is actually talking to them, but in this basically positioning arrangement, which has been forced by the users themselves, it's as if user A is looking at another user. So the way we want to make sure is we want to make sure that this relationship, relational and positional this orientational and positional relationship is held within all users of the telepresence experience. So how do we address this challenge? The goal one is going to be to locate the maximum mutual space. The way we do this is we perform a semantic segmentation to determine the bounding blocks of each object of their room. And with this, we intend to locate the sandable spaces. Sandable spaces are basically the volume of the room in which no object located within a human height range is present. And the user movement can be performed freely without the risk of colliding with the object in its surrounding physical environment. We then calculate the sandable space by simply subtracting the area of which the object occupies in a room from the room itself. We do this with all the rooms. And next, we define a rigid body function G, where theta describes a transformation vector. So then we run a genetic algorithm, optimization algorithm, to determine the optimal theta of each rigid body motion. So the area of overlap between the boundaries becomes maximum. And if we map the mutual space back to the rooms shown here in the blue area, where all users stand or walk within the blue area of their own space, they are guaranteed not to cause virtual conflicts or line of sight mismatches within each other's spaces. Now, to add a little more flexibility and increase mutual usable spaces, we also define sittable spaces. Sittable spaces normally extend the standable spaces by adding areas where humans are able to sit on, such as sofas, chairs, and beds. Again, if we go through the same process, this time with sittable spaces, We observe larger mutual areas, which users can stand, sit, and walk and move around in those spaces without worrying to cause any unwanted collisions on other remote rooms. So we wanted to implement our proposed framework on some real-world data sets just to see how it works. And we chose the Matterport 3D dataset for this, which includes a wide variety of residential houses and diverse styles and room functions. As you see here, the standable areas are indicated in green and the non-standable spaces are colored in red. And here, the sittable spaces are visualized in yellow. Again, green showing the standable space and red being non-standable space. Moving to identifying the mutual space between multiple rooms, this illustration shows how our genetic algorithm is gradually improving the results and expanding the mutual area and higher generation values. And here we show the mutual ground in blue after 48 generations of the search between these rooms. But then the question arises, what if we need more mutual space, right? What if it's just not enough and the identified mutual grounds are too small for the remote communication purpose? Say you want to play a game or inspect an object between the participants where the object doesn't fit the mutual boundary. What do we do? And that brings us to our second goal, which is rearranging the furniture so that we increase the mutual space while minimizing the overall effort to do so. And the effort of each move is basically calculated by multiplying the distance of the object's translation by the object's weight. In simple terms, moving a bed is considered to have a higher effort value when we compare to moving a chair for the same distance. So again, the goal is to slightly manipulate the room layout to increase mutual space with minimum effort. To simplify this process for the user, we define increased steps, where each step, the goal is to achieve 10% additional mutual space from its previous step, while maintaining the minimum effort to do so. Now, let's take a look at how furniture manipulation system works in an example. Again, we use real-world scenes from the Matterport 3D dataset for this experiment. We have a family room, an office, a bedroom. First, we extract the standable and non-standable spaces using the methods previously explained. Next, by utilizing our proposed mutual space identification method, we can locate the maximum mutual ground between the three rooms. We then use a strength Pareto evolutionary solver to run the optimization for the two objectives. So effort over here is shown in a vertical axis and the mutual area is shown on a horizontal axis. The mutual area on the horizontal axis, which we want to increase. So when we plot the rearrangement solution space, we can find the initial arrangement point on the Pareto frontier with the e-value of 0. Then by increasing 10% of area in each step, we find the rearrangement solution which satisfies the increased area goal and holds the lowest effort value in that step. And as you see, after 5 steps, we significantly increase the mutual space between the rooms while minimizing the effort required for the furniture rearrangement. Finally, to have a better understanding of how the users would experience the system's output, we deploy our method on a Microsoft HoloLens as an augmented reality application. For the target spaces, we scanned our office area and chose a conference room, a kitchen, and our main laboratory space for our experiment. We also provided the bounding box and semantic labelings for the model. The system then calculated the standable open spaces, visualized here in green, and the mutual spaces seen here in blue. Here you see the view from the HoloLens in the kitchen. We visualize the mutual space boundary with an offset of 40 centimeters of the ground so the user can clearly relate it to it. And here you see the main laboratory itself. Again, the blue area indicates that you can freely move around in this boundary without causing conflicts in the room. Finally, you see a floor plan view of the space with different screenshots taken in different locations of the HoloLens headset. So to talk about the limitation, of course, in our current version, the increase in steps may not have any continuous relationships with each other. For example, in step 1, you might be moving a chair in a certain direction to achieve minimum effort. But if you then decide to move to step 2, it doesn't take into account step 1's transformation. The next limitation is that our current system doesn't automatically take fixed position object into account and should be defined manually. We also currently use generic data provided by moving companies to estimate a weight of objects given its type. However, objects from the same type may have various weights, and therefore it would be important to integrate correct values to achieve more accurate results. And finally, for future steps, we definitely want to perform more extensive user studies. We definitely aim to develop this tool for a cross-platform AR/VR interface, and also use more robust floor planning methods for future manipulation. And with this, I want to thank you all for listening, and please feel free to ask any questions for our workflow. Thanks again.